problem, where's he was here, I just talked to him.
So, Casey, he's here. I
just
walked right behind him the entire time because he's good to plow half of the hallway.
Okay, that's it. All right. So let's talk about number 3. The differential equation was, as we get into this farther with the, reviewing and getting ready for the AP test, the finals, that kind of thing, you start to recognize that the free response questions tend to come, there's 6 of them, and they tend to come from kind of the big ideas of calculus. The multiple choice questions get into a lot of the details. You get into your trig review, especially the no calculator, your trig and your, a lot of that pre-calculus stuff and a lot of those little things. But the free response, typically you can kind of predict. You're going to have a differential equation problem, usually. Now, it might involve a slope field. Not every year is there one with slope fields, but a lot of times there could be a slope field involved with it. But something with a differential equation like this one. There's usually going to be one with some chart stuff, like I think number 5. Was it number 5? Got a lot about increasing, decreasing, concavity, that kind of stuff. A lot of the chart stuff. That's pretty typical. You usually have one like we did yesterday with the sand and the bin, the integral. Somehow with an integral of, you've got a rate and you want to find how much sand, went in and went out and whatever. So that was using integrals. That's usually a big one. There's going to be one that has areas, region, I think number, was it 6 or 4? 4. Then number 4 have kind of a region, had some graphs, some intersecting things, and there was some region, asked some questions about that. Sometimes, now this one didn't, but sometimes it'll be the volume, the one we've been skipping, the volumes of solids, that kind of thing. So there's usually that's going to be in one of them. And those are kind of some of the big ideas, absolute max and min, that kind of stuff, maybe some sort of a justification of an absolute max list of candidates kind of thing. If you go back and look at the main, big topic things that we've covered, those are usually going to be in the 6 free response questions. So the more of those we do, the more familiar we get with them, the better. And that's half your grade. I mean, that's half the free response on our final. We have 4 of them, 2 of them are free response, right? That's half your grade on the finals. And same thing on the AP test. Those 6 free response questions make up half of your grade. And then that both sections of multiple choice together make up the other half of the grade. Okay. All right. So anyway, here they talk about is estimated that our current constant rate of consumption, which is C sub 0 gallons per year, the oil supply of the earth will last 200 years. Okay, so if we keep consuming oil at our current rate, the oil will last for 200 years. But will we keep consuming oil at our current rate? Chances are not, right? More people, and so forth. Now, there's a lot of talk about conserving energy and green energy and using solar and and trying to, and wind energy and stuff like that to try to reduce the amount of oil that we use and fossil fuels that we use. But typically the rate has been increasing, okay? So they're saying that the rate of consumption, C is the consumption, which again is gallons per year. So C, it's important to recognize, C is gallons per year. Okay, C sub 0 is just a constant. That's just a number, right? That's the rate we're using it right now. Okay, that's I think the hardest part of this problem is that C sub 0 number. If they would have just put a number there, I think this problem's much easier. But the rate of consumption is increasing at the rate of 5% per year. That is C prime, right? That's the rate that C is changing. So that'd be gallons per year, right? So we understand what we're talking about. C is gallons per year. So I always think it's important in these story problems to think about your units. Okay, so we have this, C prime is equal to 0.05 C. Okay, all right. So that's our differential equation. I can even write it with our prime notation if it makes us feel a little better. Okay, but that is, okay. Now, does that look familiar at all? Isn't that the y prime equals ky? right? Now later, here in chapter 7, we're going to learn how to solve this differential equation. But for right now, we're just going to say, hey, we've memorized it. Okay, we've memorized that that is a e to the kt. So I'm actually going to jump to number B, and they say this: show that this is c equals this. In other words, our original function is c, right? Our original function is c. So by solving this differential equation, we'd be finding c equals. Well, we know this is y equals a e to the kt. So in this problem, this would be c equals a e, and then k would be 0.05 t. And then we need to find a, so we need an initial condition, right? Well, what's our initial condition? Our initial condition is what? What value of c do we know? Well, we know right now at time 0, c is what? C sub 0, right? I mean, it's not a number, it's c sub, that's what c sub 0 is. That's our rate, that's our c value right now. So we know that c sub 0 is, c of 0 is c sub 0. So that means if I put a 0 in for t, e to the 0 is 1, so c would, and then c is c sub 0, so a is basically c sub 0, okay? So based on that, I can just erase the a, and I can put c sub 0. And so that's all we'll do for now. Now later, like I said, when we get to chapter 7, we'll learn that how we could actually solve it. So they wanted you to actually solve it, okay? But we haven't learned that yet, so we won't. Okay, so that's all part B is about. All right, now the key to getting part C though is now doing part A. In terms of C sub 0, how many gallons are currently available? Remember, C is gallons per year. Okay, so how many gallons do we currently have with the information that we're given in the problem? Okay, 200 C sub 0. It's much easier than you probably think. I mean, you know, if you go through this, you're probably thinking there's some whole big antiderivative, something, I want to get gallons, I'm going to have, you know, but no. They said in the problem that we're using C sub 0 gallons per year. Let's say that's 5. Let's just say we're using 5 gallons per year, okay? And it's going to last for 200 years. So how many gallons do we have to have? If we're using 5 gallons every year and it's going to last for 200 years, 1,000 gallons, 200 times 5, right? We've got to have 1,000 gallons. We're going to use 5 gallons every year. That will last 200 years. So it's just 200 times how many gallons we're using each year. So it's 200 times C sub 0. Okay? All right. So that is our current number of gallons. Now, what should we call our function that is gallons? If big C is gallons per year, what would be gallons? Bigger C? Great big C? You know, it's kind of hard, right? I mean, if big C, if capital C is gallons per year, and we want to do gallons, they have to derive that. It's hard to have a notation for it, right? Great big C, whatever. Okay? Or G, yeah, but G for gallons. Okay, G will be gallons. Let's do that. That's a good idea. So G sub 0, right, would be that right there. In other words, that's how many gallons we have right now. It's kind of like the sand problem, right? Remember we talked about the tank being empty, right? We need to know how many gallons or how much sand we started with if we want to know how much we're going to have later. Well, same thing in this problem. We need to know how many gallons of oil we have now, and that's what part C gets into. Okay, so if no additional oil, but you know, we don't have to label that. I mean, we don't have to. You can just put 200 C sub 0. If no additional oil is discovered, how long to the nearest year will the oil supply actually last? Show how you arrived at your conclusion. Okay? So, ideas. So this, remember, is our, remember C here, this is gallons per year. So, ideas. It's going to be using a combination of this and this. What do you think? We want to know, we're answering a question about gallons. In part B, B, we have an equation for gallons per year. So what? Antiderivative or an integral? Is this a calculator one? This is a calculator. Okay. So let's do it as an integral. So what would our integral be? From what to what? 0 to what? 0 to some number we don't know, right? That's what we're trying to find, right? So let's call that x. Yeah, that's good. Let's call that x. And then what would go in here? C sub 0, right? Now we got to do more than that because we've got an x we're trying to find. So that's got to, right? That's got to equal something. 200 C sub 0, right? In other words, but to understand that, we got to understand what this is saying. What is this saying? This is the rate that we're consuming in gallons per year. So if we do the integral of that, what does that give us? The amount of gallons we consume, right? If this is the rate that we consume the gallons in gallons per year, then the integral is going to be the amount of gallons we consume. And for us to run out of oil, how many gallons do we have to consume? All the oil that we have, right? That's what we did in part A. We have 200 C sub 0 gallons available. Yes? No. Because this is an unknown. We don't want this to match this, actually. See what I mean? Okay, so this is 200 C sub 0. Now, let's make sure now. I just thought of something here, and I got to make sure. How long will it last? Yes. It seems to me in the past, there was a time we had a discussion in this problem, so I think I've got this right, but where we set that equal to 0. Because the thinking was we want to know when we'll have no oil left. But I don't think that's what we want though, right? Because this is, we got to think about what this represents. This is the rate of consumption, right, of us using the oil. So this integral is going to be the amount we consume, right? This is going to be the number of gallons we consume. So we don't want to set it equal to 0. We want to set it equal to how many gallons we're going to consume, right? And that is all the oil we have. If we're going to run out, right, then it would be when we use all that. Okay, so now C sub 0, remember, is just a constant. Can I pull that out in front? And then when you pull it out in front, can't you just cancel it from both sides? You just divide by it. So now the C sub 0 is not going to be an issue. And now we can just type this into our calculator as a solve. You guys will have it done before I did. I didn't have a program open. Integral. Whoops. Equals to okay. And I don't know, some of you may, well, I told you we would go over this one, so you may not have looked it up, but yeah, that's what they have said. Okay, so, and that's that's just 5, so that's quite a difference, right? Instead of 200 years, right? Just increasing the rate at 5% each year. It changes it to 47.958. Okay? Yeah, yeah, exactly. You know, there was a video of, I need to look that up and find that and show that to you guys. About, there's this guy, this college professor in Boulder, Colorado, University of Colorado, was talking about oil consumption. Well, he was actually talking about, yeah, he was talking about oil consumption. He was talking about population of the Denver area. And he was talking about the magic of 7%. That 7%, like, you would double every 10 years if it grows. I mean, there's a rule in finance about 7%. 7% growth, then the amount doubles every 10 years. And so, and he was talking about that, about the growth rate. So you talk about 5% per year. I mean, when you talk about that amount, I mean, what actually happens over a short period of time, the amount doubles. So the amount you're using doubles. And he was talking about the space. And he gave this example, and I'm going to screw it up because here I'm trying to do it off the top of my head here. But he was talking about this example of using population, and he used the example of, oh gosh, dang it. I'm not even going to attempt because I'm going to totally ruin it. So I'm going to look it up. While you guys have some work time today, and I'm going to find it and show it to you. But this power of doubling, we've talked about exponential growth before, but it's pretty interesting when you think about it. So I'm going to look that up and show it to you. But it kind of fits in with this idea that just a small amount of growth, and if that's actually how much oil we have, which I don't think that's accurate, they just made that up, but nobody knows for sure probably what we have. There would be the right answer. So back to the calculus part of this. The key again, I think that was units. Think about the units. Think about what this stands for. Gallons per year. This question had to do with gallons, okay? And so we want to be able to set that up. But it was without answering this first part and getting that, it gets hard to do the rest of it, especially part C. Okay, any questions on any others in this? 4 or 5 that you were supposed to kind of make some attempts at? Any issues of parts of those you want to talk about? Four? Any part? All parts? I mean, it has a little bit of the look of Shanghai, doesn't it? I mean, I don't know if it does. I'll be honest, I haven't done this one for a while. But, I mean, what you have is you have a tangent line that's touching. You got a couple different points on the tangent line, but you don't know them, right? But you know they have the same slope. So you know the slope of this line is a constant. So you know the slope of this graph has to be the same as the slope of this graph at those points. Okay, we do know the point where they intersect right here. And we do have their equations right here. So this one is F right here, and this one is G right here. Okay, so the first one says show that A is equal to B minus 3. Then it says find the numerical value of both A and B. Then write the equation tangent line. So these all kind of feed off of each other. Okay, so I think this could start out. Well, you guys tell me, somebody tell me, because I'll start doing it some big long way, and then Maddie will say, well, you could have just done that. So, anybody? What? Maddie? Did you?
I said them equal to each other, but it didn't work out.
But it set what equal to each other? The F and the G?
Yeah.
Yeah. Now, if you set them equal to each other, that's going to give you this point right here, right? Did you do derivatives? Wouldn't derivatives have to do? Right? Isn't that what would have to be equal? Is a derivative at this point would have to be equal to the derivative at this point? Because they both have to have the same slope. They both have the slope of this line. Okay? So if I do the derivative of F, I get 2x. And I did not work this out ahead of time, so I'm just this is my first thought at this. And it might not work. We'll see. Bringing 2 down in front. So you got that. Okay? Derivative inside is just 1, so that'd be 2x minus 6. Okay? All right? And so that means at point A, right, that's the F graph. So at point A, what's this slope? What's the slope at this point right here? 2a, right? Since the derivative is 2x, at point A, the slope would be 2a. And then what's the slope at this point? You'd put a b into here, right? So the derivative of the g-graph is 2x minus 6. So at point B, you'd plug a b into there, and this is 2b minus 6, right? And what do we know about this and this? They should be equal because they both represent the slope of that line. So 2a has got to equal 2b minus 6. So divide by 2. A's got to equal b minus 3, right? So that's the idea there. And again, the key was that the slope of those two have to be the same. The slope of that line is a constant. And so any point it touches on the curve, remember, because that's what derivative is the slope of the tangent line, right? So the derivative is that. All right, so then find the numerical value of A and B. Okay? So now we have to do something a little different, or a little addition. Wouldn't that be the Shanghai thing? Couldn't that do it for us? I mean, I'm trying to think here. Or is there something easier? Doing the slope at these 2 points seems kind of... Oh, no. Yeah, since we know this, since we know A is equal to B minus 3, then this would just be... Yeah, we could do the slope between those 2 points, which would be... So we could do... But we'd have to make a substitution. In other words, let's take this and substitute, right? So this would be the same as the point B minus 3. Oops. If A is equal to B minus 3, then this would be the point B minus 3, and then B minus 3 squared minus 3, right? I'm just making a substitution so I don't have two variables. So I'm going to replace A with B minus 3. Now let's do a slope here. So we would have, let's do this bottom one, subtract that. So B minus 3 squared minus 3 minus B minus 3 squared. That'd be the top. Oops. See what I did there? I just subtracted the y's. For some reason I feel like I'm doing more. I think this should work. And now subtract the x's, so that'd be B minus 3 minus B. Can this be right? Isn't that just negative 3 over negative 3? How does that feel wrong? No, I didn't have to square it. I mean, B minus 3 quantity squared, subtract B minus 3 quantity squared, that's just going to disappear, right? Looks like that slope did be wrong.
Maybe you should try it the other way.
Well, but what I'm saying is if the slope is 1, if the slope is 1, then what do you know? That means 2a's got to equal 1, right? So A would be 1/2. And 2b minus 6, well, I could just, once I know A is 1/2, then I could come over here. I wouldn't have, but I could just say, okay, and then this has got to equal 1, this slope's got to equal 1, so 2b's got to equal 7, so b's got to equal 7/2. Or I could have just plugged it in here. If A is 1/2, I can add 3, and I get 3 1/2, same thing, 7/2. Yeah, I think that's right. I mean, looking at the graph, now they would always tell you this is not to scale, but I mean it looks like B is about 3 1/2, and it looks like A is about 1/2. I mean, so it seems to make sense. I mean, this makes perfect sense that we should be able to do this. If A is equal to B minus 3, you should be able to substitute it here. You've got two different points. You should be able to subtract them to get slope. Now, what I was going to do is Shanghai, though, remember, was two different ways to do slope, right? subtract the y's, subtract the x's, and then set that equal to, so I was going to set that equal to this. I was going to set that equal to 2b minus 6 is what I was going to do, right? Because I expected there to be some b's in here, is what I thought would happen. I didn't think they were all going to disappear, right? So this is one way to do the slope. That's what Shanghai was, slope between the 2 points, and then set that equal to the derivative, right? Because that's also the slope. And since I want b's, I'm going to use 2b minus 6. Well, what happens is you end up getting this whole thing just ended up being 1. So I got 2b minus 6. So I got 2b equals 7. And I got b equals 7 halves, right? 3 1/2. And then once I had b equals 3 1/2, I just plug it into here. 3 1/2 minus 3 would be 1/2, right? So that's what I was planning to do. It just felt weird that all the b's dropped out. And when that happened, I was thinking, wait a minute, I might be doing some circular reasoning here. But I think it does work. Okay, because if I had just done that. But that's what Shanghai says to do. 2 points, do the slope between them, and then do the derivative, which is also the slope. Set those equal to each other, and then you can usually solve. Okay, and so that's what happened then. All right, so that's what we got. So we got A and B both. So it was a little bit of a Shanghai situation. All right, now write the equation of line T. Well, now that we know these points, I mean, now it's easy because now we know this is 1/2. And this would be 1/2 squared, it'd be 1/4 minus 3. What's that? Negative 2 3/4. Wouldn't that be that point? And then this point is 3 1/2. And then 3 1/2 minus 3, it should be 1/2 squared, which is 1/4. And it looks about like that's about what that point is. So now that we know those 2 points, writing the tangent lines easy, we already know the slope. What was the slope? We just saw the slope was 1. So this is just going to be y equals, remember our way of doing this, 1, and then pick either one of those points, doesn't matter. Okay, just write your y, put your slope in for m there, pick either one of those points, put it in for the a and the b there, and you got that. Okay, I'll put this sign on line. I've got a handout and a sign sheet. Because I forgot what chapter 7. I haven't done it yet. I haven't printed it out yet, so I'll just have to show them. Okay. All right. So there's the equation line. So once we know those points, that's easy. And then the last part, set up but do not evaluate an expression. Now here's where this part we're going to we'll come back to later today. Okay? Because we're going to learn about this. How do we find this region? How do we do a region like this, especially where part of it's below and part of it's above the x-axis, all that stuff? Okay, how in the world do we do that kind of a region? Okay, so that's the next thing we're going to do right now, and then we'll come back and we'll set up that part of it. Okay, so get your notes out. Get your notes out, and we will talk about this first part here of chapter 7. Now, you don't have to write this down here, but so what we're going to talk about today is just like that problem we were just looking at. How do we find this area between, curves, different curves? Right now, what we've done is you got a curve like what I have, and we've just done the area underneath it, okay? But all that work we did with sigmas and rectangles is really going to pay off now. When we get into chapter 7, which is our uses of the integral, we'll really be able to think about them as this, okay? When we set up an integral, we're adding up a bunch of areas is what we're doing. And that's how we want to think of integrals. We're adding up a bunch of areas. And so if you look at how we did this, how did we handle, why was this a negative area? Well, if you think about it, we would take the y value times the width. Well, what is this y value right here? It's negative. So when you take this height of this rectangle, it's a negative value. You multiply by the width, you get this area. That's going to be a negative piece of area. And then likewise over here, you take this height, that's positive, that y value, times that width, that's going to give you a positive value. And so when we do an infinite number of these and add them up, that gives us the integral. And that's why we get negative, both negative and positive areas. Okay, so if I needed to do, if I was going to do, now this you might write down in your notes. So here's two curves. One is x squared, and one is cube root of x, which I've written x to the 1/3. Now we're going to get to use our calculators a lot on these problems. We're going to be typing a lot of integrals into our calculator. We're now getting to the point where the whole purpose of these problems is to get the right integral set up, and then we can use our calculator to find it. A lot like we did on the oil problem. We set up the integral, and then we just type in our calculator to get it. So what I'm looking for is this blue area here. Now, we've already done this problem. We've already done this problem in kind of a roundabout way, right? Haven't we seen this before? And how did we handle it? No. Yeah, didn't we say, let's take the top one, this cube root, let's find this black area. Remember that? We said, so let's do the integral. Now we need to know this value right here. We need to know what that point is, so we need to know where those intersect. Okay? So let's find that right now. So on your calculator, how would we find where those intersect? Where they're equal to each other, right? So let's do a solve on our calculator. Let's solve. So you're going to be doing a lot of this. You know, up until now, our integrals from what to what have been pretty easy to figure out. But now we're going to have to, a lot of times, find out where they intersect. So where does x squared equal x to the 1/3 power at 0 or 1? Okay, well that turned out pretty easy. Probably could have figured that out on my own. But that is at the point 1, 1. Makes sense. 1 squared is 1, cube root of 1 is 1, and then back here at 0. Okay, so we would do the integral from 0 to 1 of cube root of x, and we would find that area, that's black, and then do what? Find the area under the parabola, and then we would subtract those, right? So we would do this. So we would find that black area, and then we would find the red area, and we'd subtract those, and that would leave us the blue area, right? Now, one of the things we did learn is that when you have an integral that's added or subtracted, you could split it apart, right, into separate integrals. And then likewise, we could put this into just one integral as well. We could have just made this, right? We could have just done that too, couldn't we? Okay, we could have just done that. Now, the interesting thing about doing that is when we write it this way, the calculator doesn't know. I mean, the calculator doesn't pay attention to this. But when we write it this way, what we're really talking about is this. We're talking about black area minus red area. But if I just gave you this integral, would you be thinking of it that way? Or would you just think of this as a function, right? You'd be thinking of this as some function, who knows what it is, you know, blah, 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 whatever. And we would be doing this area, and wouldn't you just be doing this area from 0 to 1, the area between it and the x-axis? Sure, and you'd be right. But guess what? This area must be the same as that area, right? Because remember, a definite integral is just a number. This is just a number, like 7. 7 can mean a lot of different things. It could be how many dollars I have in my pocket. I wish. I didn't have 7. Okay? It could be the number of bonus points I give you for not being tardy. Oh no, that's not. Okay? It could be, 7 could be a lot of different things. Right? It could represent. So, same thing here. This definite integral can represent a lot of different things. Matter of fact, we just did a problem where the integral represented the gallons of oil we consume. Right? That's what that represented. Okay, this integral could represent this blue area, but it could also represent this piece of area too. Okay? All right, anyway. So when we type in a calculator, it doesn't know. It's not paying attention to that. But that's how we did it. Now, the problem is, does that help us attack this area? Would we be able to say, oh, okay, let's find the, you know what I mean? I mean, if we just did the area under this integral, it would be like this little piece and this little piece, and how would we do this piece from here to here? And we would have to divide it up into all kinds of different areas, regions. It would be just, I mean, we could probably do it, but it would really get kind of interesting, okay, and kind of messy. So there's an easier way. So what we want to do instead of this is we want to think of rectangles. We want to think of rectangles. Let's think of that red area now as adding up a bunch of different rectangles. Now, I've drawn in left rectangles, but look at this one. What would be the height of that left rectangle? Well, no, it's not. This isn't the scale. Remember, this is one right here. Okay? But how would you find the height of that right there? You would find this y value, and you would find this y value, and do what? Subtract it. You would take the top y value minus the bottom y value. Now let's call this one f, and let's call this one g. So the top one is f. So wouldn't this be f minus g? Wouldn't that be your height? And then your width would be your delta x, right? And what would this height be? F minus g. Now what would happen if we do g minus f? It'd be negative, wouldn't it? How do we make sure that it's always positive? Take the top y value minus the bottom y value, right? Won't the top y value always be bigger than the bottom y value? So if you, now why would you want to make it always positive? Couldn't it be negative? That's the next question we got to answer. Is this, when you do an area between curves, like on this problem, does this down here count as negative? Well, the answer to that's going to be no. If we're going to do an area between curves, we are going to be doing a positive value, because here's what they're asking. When they ask in this problem, find the area of region R. If I took this whole picture and shifted it down so it was all down here, would R be any different? Would the region R be any different? If I took this line and these two parabolas, shifted the whole picture down, would region R change? Or if I took the whole picture and shifted it up, would region R change? No. Now, that's not true of a, oops, that's not true of a graph like this. If I took this graph and did this area right here, and now I took this parabola and shifted it down, would that area change? Sure. And I shifted it up, would that area change? It would change, because we're doing the area between this fixed thing. So when we talk about area between curves, there's not going to be any negative. The x-axis is not going to even matter. Okay, so when we take that problem in your packet, the fact that part of that's below and part of that's above, we don't even care about. We're not even going to pay attention to it. Okay, we're not even going to pay attention to that. So area between curves is different than the area under a curve. The area under a curve is like this. What it really means is the area between the x-axis and the curve. Okay, in that case, negative below, positive above. But when we do area between curves, above, below the x-axis, not going to matter. Okay, so we're always going to want to do the top curve minus the bottom curve, like so. So we take the top y value. So basically that gives us our height of our rectangle, and this gives us the width. That's the dx part, right? So we got height times width, which is area. The integral is going to add up those areas. So when we set up this problem from now on, we will simply just go right to this. We'll say, okay, 0 to 1, we're going to take the top curve, which is x to the 1/3, minus the bottom curve, which is x squared, tack on a dx at the end. So this is like height times width, and there is going to be our integral when we do the area between curves. It's simply going to be top curve minus bottom curve, which was what happened here anyway. We did the top curve area, bottom curve area, that happened anyway, but now it's going to work even if we move this around, even if we take this region and move it around, okay? It gets more confusing to think of it like we did here, black minus red. If the x-axis gets involved, then it gets really confusing. It's going to work no matter what, but the best way to think about it is this. So what you'll see me do, so right now, so this would be good to put in your notes. So when we're doing area between curves, now number one here, notice it says they're vertical strips. You're going to see what I mean by vertical strips. Basically, that means vertical rectangles. Now we're going to start calling them strips because how many rectangles do we want to get the true area? Infinite, right? Infinite rectangles. So they don't really look like rectangles. They're more like little tiny strips, right? Little tiny line. I mean, if you had an infinite rectangle, you couldn't even see them, right? It'd just be like a whole bunch of little strips. So we'll talk about, we'll just draw in like one strip to represent what a rectangle would look like, and that'll help us. And we'll talk a lot about top minus bottom. Okay, why top minus bottom? Because we want it to be positive. So the top y value minus the bottom y value. Okay, and then of course the dx is the width, and so that gives us area, and the integral adds it up because the integral is like the sigma. Okay, now the bottom one is if we do horizontal strips. Now, why would we want to do that? Well, you're going to see in some regions, in some areas, it's going to be easier if we add up horizontally rather than vertically. So what we want to do there instead, notice it's in terms of y. Notice it says dy there. And notice my function says f of y and g of y. Well, what that is the x coordinate there. If we're doing it horizontally, if I want to know how wide this strip is, right? If I want to know how long that strip is, I want to take the right x coordinate and subtract the left x coordinate. And so that's why it says right curve minus left curve, because I want it to be positive. This x coordinate on the right is bigger than this x coordinate on the left. Okay, I'm going to show you on a sketch pen. Yes?
What if it doesn't stay on one curve? What if it doesn't stay at the top curve?
Yeah, that's a great point. What happens if the top curve then crosses and then becomes the bottom curve? We're going to have to split it up. We'll split it up into different parts. Okay, that's what we'll do. We'll see some examples of that here in a second. So, let me show you here. All right. So, if all right. So, if we have these two graphs right here, okay, and we want to find this area. Again, we're going to ignore the x-axis. Okay? So, think of that red vertical strip there as all those different rectangles, and we're adding it up from the left edge to the right edge. Okay? Okay? A little slower. Okay? So we're wanting to find, so if you look, and now this gets to kind of what Jamie was saying, if you look as that goes across, notice that the top y value is always on the blue curve and the bottom y value is always on the brown curve, right? So that red strip will always have a height of this y value. And what is this y value? Remember, this is y equals 5 minus x squared, right? So when I ask you, what is this y value right here? 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 What I want you to say, when I ask you what this y value is right here, I want you to say, it's 5 minus x squared. Does that make sense? What is this y value right here? It's 5 minus x squared. How do I know that? Because right here it tells me y equals 5 minus x squared. Everywhere on this blue graph, y is equal to 5 minus x squared. What is the y value right here? X minus 1. What's the y value right here? X minus 1. What's the y value right here? X minus 1. Okay? So when I draw this red strip right here, and I want to know what's the length of that strip, it's this y value minus this y value. What is this y value right here? 5 minus x squared. Minus this y value. What is this y value right here? X minus 1. Very good. Very good. Okay? Every y value on the blue curve is 5 minus x squared. and every y value on the brown curve is x minus 1. So this strip height is this y value minus this y value. It's weird because they're y values, but they have x's in them, right? But that's because it says y equals 5 minus x squared. The y value changes every time you get to a new x, right? So that's why it should have x's in it. Every time you go to a new x, new y value. All right, so that is the height of that strip. What's the width of that strip?
I'll have to find those two graphs equal.
Oh, what do we call the width? Delta x. But when you write it as an integral, what's delta x become? Dx, right? Because you do an infinite number of them, it's nothing. So that width is changing x. It's delta x. That's going to be the dx. So you tack a dx on. So you got, there's your rectangle height. There's your strip height. There's your strip width. That's the area of one strip. How do we get the whole area? How do we get all these strips? We add them together. What do you use to add? Sigma, but yeah, when you have an infinite number, the sigma becomes... Well, your timing's awful. When I do this, you're supposed to say it. When you do an infinite sigma, it becomes... Who said that? Say it louder. When you do an infinite sigma, it's an integral, right? An integral, it's even shaped like an S for some, right? It means add. The integral is an adder. From now on, an integral, think of it as an adding machine. Go back to my very first picture. Okay, and, oh, and by the way, this will go from where to where? Well, I don't know. What's it say here? Negative 3 to 2. And that will be that red area. Okay? Because what are we doing? Our integral is an adder. Right? That's what it does. It adds up these areas. So we're going to add up these strips. Okay? All right. Vertical strips. Now, oops, back to this one. Let's see what this one looks like. Oh my goodness. From negative 1 to 3. This is what Jamie was talking about. It changes, doesn't it? So here the brown graph's on top. Then the blue graph's on top. And then later on over here, no, I guess at the edge, the blue graph's on top. So what are we going to do? We're going to split into two parts. In the first part, what's this y value right here? Good. X cubed minus x squared minus x plus 5 minus this y value, which is? Right? Top minus bottom. But then, so you'll go from here to here with that integral, and then you'll switch it. Right? Then you'll switch it. And then it'll be the blue minus the brown. Okay? And then the width is dx. All right, now, let me see if we can find one. Aha, here we go. Now, let's look at this one. Ant. All right, so, vertical strips. What is this y value right here?
6 minus x.
What is this y value? 1 over x, right? So every one of those red strips, right? Every red strip, when you go along, the red strip touches the blue curve on top, the brown curve on the bottom, right? So its height is going to be 6 minus x. So let's try this on our calculators. So let's go, so it would be the top y value is 6 minus x minus the bottom y value. What's the bottom y value? 1 over x, because it says it right here, y equals 1 over x, right? Y equals 1 over x, so this y value is 1 over x. This y value is 6 minus x. This y value minus this y value gives me this height. What's my width? Well, you guys are slow on that one, but you'll get better. You'll get better. The width, dx, right? The width is dx. Height times width, that's area. The integral does what? Adds them up. The integral adds up all those strips from? Oh. Yeah, I should have changed those numbers. That's okay. From 0.172 to 5.828. Do that on your calculator for me, please. 0.172 to 5.828. $13.445. Are you getting that? Okay. 13.445 is that area. Now, oh shoot. Oh, here it is. Oh, dang it. Ah, shoot. This is the one I wanted to do. Okay, that's fine. That's fine. Okay, let's do this one. This is a little practice. Isn't bad. Okay. Now, same thing. Top curve. So back to what Jamie said. It's very important when you look at a region that you got one curve that's always on top and another curve that's always on the bottom. Right? If it's not, then you're going to have to split it up. Okay? Well, in this case, our top curve, what's this y value right here? 2x. What's this y value? X cubed over 2. So the height is going to be 2x minus x cubed over 2, right? This y value minus this y value. Okay? The width?
Dx.
Dx. That's the area of one strip. Right? We can put parentheses around it. We don't have to. How do we add up all the strips? Integral from
0 to 2.
0 to 2. Type that one in your calculator. Now, and then we're going to do horizontal strips. Then we're going to talk about horizontal strips. Okay? And how that changes it. Okay, what do we get? Oops. 2. Okay, area of 2. Now, let's find that same area, but let's talk about it as, so here's the same area, but now look at our equations. This equation, now what's another name for f of y? X. Because f of x, another name is y, right? This means you plug in a y and get out of x. We're just reversing. So this is x equals 2y to the 1/3 power. Now, where's that come from? Well, that's the blue graph. Well, just a minute ago, the blue graph was this. Wasn't it? So how do we get it in terms of y? We solve for x. So we're going to multiply by 2. We're going to do the cube root of both sides, which is the same as 1/3 power. That's how that became that. They're the same graph. They're the same graph. Our other graph was y equals 2x. So if you solve for x, you get x equals y over 2, which is that graph, right? So these two are, again, you're probably saying, why would you do that? Why wouldn't we just do it like we always do it in terms of x? Well, some problems are going to be way easier and possibly only able to be done with horizontal strips. Okay? And so that's why we're going to want to do it. So let's look at this. So there's our graph. Now, doesn't it make sense that we can also get the area by finding the area of this strip and then adding up all the strips? Doesn't that make sense? I mean, that should do it. Instead of adding up a bunch of vertical strips with an integral, let's add up a bunch of horizontal strips. It still should give us the same area. So the question is, okay, what is the length of this strip? Well, it would be this x value subtract this x value, right? You ready? It would be this x value subtract this x value. Now we want to do right minus left because the right one's bigger, right? We want it to be positive. So do right minus left. So what is this x value? 2y to the 1/3 power. It says it right here. It says x equals 2y to the 1/3 power. So that's what all of the blue x's are, is 2y to the 1/3 power. What is this x? Y divided by 2. Right? So that is the length of that strip. Now, what's the width or the height of that strip? dy, because it's an up and down. So it's delta, not delta x, which is this way. Delta y is this way, or dy. Okay, so when you have horizontal strips, it's dy. Now it makes sense because we always said the dy just kind of meant with respect to. So it makes sense that if these have y's in them, that would be a dy, right? So that makes sense. So that's the length or the width, or I don't care what you want to call it, the height of that strip. It's horizontal, so it's weird to call it height, but length of the strip times the width of the strip is the dy. The integral will add them up, and then from where to where? 0 to 4. Now, in our last problem, it was 0 to 2. Well, that's because we were going this way. I always think of it this way. The strips fill the space from where to where? The strips fill the space from 0 to 2 when we go this way. But when we're going horizontally, the strips fill the space from 0 to 4. They're y values. It makes sense that when this problem is in terms of y, it makes sense that these values here are y values. Type that into your calculator. We better get 2, right? Because it's the same piece of area. So we better get 2 when we do that. So some of your homework problems, I think, are going to ask you to do both vertical and horizontal strips, like this problem, and compare to see that you get the same answer. Or they're going to tell you to do them a certain way, either do it with horizontal or with vertical strips. Now, they might say in terms of x or in terms of y. In terms of x is our normal way of doing it, which is vertical strips. Okay? In terms of y would be horizontal strips. Did you get 2? Okay? You should get 2. All right. So, back to this problem. All right. All right, here we go. This is one of your homework problems. Okay? So, let's go ahead and graph this on your paper. While you're doing that, why don't you go ahead and go to your homework paper, okay, and grab a new page or wherever you're going to do your homework and graph this guy right here. Well, unless you're not going to do your homework, I guess.
Now it's a lot harder than the ones we just did. It's not that hard. It's just
This is actually number 3 in your homework. Now notice how a couple of the equations are given as x equals. Now, if you want to use your calculator to help you draw a region, okay, then probably need to solve it for y, right? Like x equals 1 minus y squared. That's that sideways parabola, okay? Now, you can just whenever you have that, your shifts are just reversed. In other words, if you've got 1 minus y squared, that would be a parabola normally that'd be upside down, right? Well, it's a sideways parabola since the y is squared, so instead of opening to the right, it's going to open to the left. And then the plus 1 normally would shift the graph up 1, right? But what's it do in this case? Shifts it right 1. That would be right 1 because up is positive, so right, when it's sideways, right would be positive. And down is negative, and left would be negative. So what this did is it took this parabola that usually be at the origin, would open left, and then it shifted it right 1. Okay? So you can draw it out by just converting it that way. But you could also solve this for y. You'd have a plus minus square root, and then you could type it into your calculator, right? You'd have to type both halves, so if you needed to. And same with this, x equals y plus 2. Well, that's the same as y equals x minus 2, right? Or y equals x minus 2, and then you could graph it. And that's why it's a negative 2 y-intercept and then a positive 1 slope, right? And then it's got y equals 1, y equals negative 1. Now, in your book, in the examples, they use this as an example of a problem where horizontal strips would work way better than vertical strips. Okay, and this is the last one I want to do just to point this out. So we're going to do it, because in your homework you've got to do it the harder way, the vertical strip way. And just as a point of emphasis, why this be easier. So let's just do it as a practice for horizontal strips, then we'll talk about how you would divide it up. So if we look, if we look at this, okay, if we look at this picture, if you were to put vertical strips, back to what Jamie said, what happens if the top curve isn't always the top curve, right? If I was to do vertical strips and start over here on the left, well, my vertical strips here would go from here to here, wouldn't it? But once I get past here, I would have some vertical strips that would go from here down. Let's see, this is the same point as this, I guess. So here I would have vertical strips that would go from here down to here, right? And then once I got, I guess the rest of the way it would have that. And then I'd have this piece of area here where the vertical strips would do that, correct? So I would have basically 3 different regions I would have to do the area of. Now, you probably figure that the symmetry, with symmetry, this area has got to be the same as that area, right? And then this area right here, if you go down here, here to here, that's just a triangle. So that'd be pretty easy to do, right? But I'm going to want you to set up integrals with that. So basically, if you want to draw in those 3 strips there on your picture, that's problem number 3. Problem 3, now what you're going to get in problem number 3 is a little practice at reading the language as well, though. Because what it's going to do is it's going to say in part A, find the region bounded by y equals 1, the parabola x equals 1 minus y squared, and the vertical line x equals 1. Well, that would be this piece of area right up here. Right, that'd be this little strip or this little piece up in here. Then they're going to, in part B, I don't know which part is which, but in part B, they say bounded by this, this, and this. Well, that ends up being this region. And then they give you bounded by this, this, and this, and then it ends up being this 3rd region, okay? And so they break it up, and you have to find each of those as 3 separate integrals, okay? Now, here's why horizontal strips would be so much easier. Because starting down here at the bottom, if I drew a horizontal strip, it would touch the line on the right, and it would touch the parabola on the left. Wouldn't every horizontal strip I draw do that? Every single horizontal strip I draw in here will touch the line on the right and the parabola on the left. And so I can do that green region in just one integral if I use horizontal strips. So what would it be? Let's do it. This isn't really part of your homework, but it'd be this x value, which is what? This x value is y plus 2, right? It says it right there. It says x equals y plus 2. So this x value is y plus 2 minus this x value. What's this x value? 1 minus y squared. Now that's got to be in parentheses. Make sure you're using parentheses there, because you're subtracting that. So this x value, which is y plus 2, minus this x value, which is 1 minus y squared, and then the width of those is dy. And then those blue strips fill the space from -1 up here to 1. Okay, so if you type that into your calculator, you will get, now by the way, the calculator doesn't know that you were just doing a problem with horizontal strips. So if you plug this into your calculator using x's or t's or q's or z's or whatever, it would come out the same, right? It would come out the same, all right? But when you write it, you want to write it like this, okay? Type it into your calculator and you'll get that area. Then when you do your homework problem number 3, they're going to have you split this into those 3 integrals. When you add those 3 together, you will then get the same answer. Now, keep in mind, when you go to do, and I'll just give you one more bit of help, and I want to talk about one last quick thing. What is this y value right here? 1, right? Y equals 1. There it is right there. What is this y value right here? No. What is this y value? We've got to solve, not for x, in terms of x. We've got to solve for y, right? Because we need y equals, right? When I ask you what's this y value, you've got to be able to look at something that says y equals this, right? So you've got to solve this for y. That's the other problem doing vertical strips on this one. We've got a little more work to do there. So let me add the y squared over to there. Let me subtract the x. Then let me do the square root. Now that's plus or minus. Now why is there a plus or minus? Top half, bottom half. So this y value is what? Square root 1 minus x. What is this y value right here? Negative square root 1 minus x, right? Because it says right there y equals, right? So this one is going to be 1. This y value is 1. This y value is square root 1 minus x, right? That would be the height of this one. So then your integral, your dx, and then that goes, why am I doing your homework for you? That goes from where to where? Doesn't it stop right there? 0 to 1. Because once it gets past there, then the strips go down to the line. Right? Now the strips aren't hitting the parabola on the bottom anymore once it gets past 1. So that, and that's probably part A or B or C, I don't know, it's one of the parts of problem 3 right there. So that would go from 0 to 1. So that would be that piece of area right there. Okay? And then you'll have a piece down here, you'll have this piece here, you'll add all those up, and it should give you the same answer you just got for that one. All right, so that shows you that. All right, finally, last thing, when you start doing your homework, it's going to ask you to do a midpoint rectangle thing. I would not worry about that. I think on one it asks you for a left rectangle, one it asks you for a midpoint rectangle. All they're talking about there is actually divide this region up into like 5 rectangles. So you would just have to get your widths. Let's say it was 0.2, 0.4, 0.6, 0.8, whatever. And then you plug 0.2 into both equations, right, to get those y values. That gets you the height of that rectangle. Then you plug your 0.4 into both equations, subtract them, that gives you that rectangle, 0.6, right? I mean, that's how we would do, and we will probably do some, but don't worry about it on this homework, where we do some left or right or midpoint rectangles for an area between. They would just look like this. Okay, so when you get to that part, I think it's on problem 1 and problem 2, there's one of the parts that says do an M5 or an L4 or whatever. Don't worry about that part. Just work out the actual area. Okay, all right, so homework is, I'll just put it up here and then I'll pass these out here in a little bit as soon as I go get them. So there you go, top line right there.
Sure.
Check this out. These two will just cancel out.
Yeah, no, and one, and there's one for him, and one back. Oh, yeah. No, I haven't.